This playlist deals with some aspects of Eurocode 2 version 2023. Watch this channel playlist for further selected topics. This video deals with clause 8, ultimate limit state, and it's the second part on shear. You remember the 3 basic steps to calculate shear reinforcement, and the second step is when the shear stress is the applied shear stress. It's smaller than the shear stress that the concrete can take. At that moment, you need shear reinforcement. The shear stress capacity of the concrete alone is defined by formula 827. And in this formula, you see that there is a longitudinal reinforcement, rho L, and rho L is defined as usual as the total reinforcement with sufficient anchorage, left and right on the control section, divided by BWD. The shear force capacity of the concrete alone has a minimum value, which is called tau RBC min. The longitudinal reinforcement ratio had an upper limit of 2% in the version of 2004. In the present or in the code of 2023, there is no mention of an upper limit. So we can ask why. The value of D in this formula, 827, may be replaced by the mechanical shear span, AV, for effective shear spans smaller than 40. These are 2 new concepts, mechanical shear span and effective shear span. The mechanical shear span is equal to the square root of what is written in formula 829. The effective shear span is the ratio of the bending moment divided by the shear force and then the absolute value of it, but the effective shear span must always be bigger than V. Now we can detect small problem when you have an isostatic beam, single span, with a uniform distributed load. In midspan, the shear force is 0, or you can say when the shear force is very small, then when VED is very small, then ACS, or the effective shear span, will be very large. And when the effective shear span is very large, then the mechanical shear span is very large, and then D will be very large. And when D is very large, then the shear stress will be almost 0. So this cannot be right. When you have in midspan a 0 capacity of the concrete alone, that's not right. This is why there is a limit on the effective shear span ACS, which is 4D. But written like this, it's not so easy to understand it immediately. So that's why I propose to clarify this formula 8.30 by replacing it by saying that the effective shear span must be limited between, or must be situated between D and 4D. Then it's much clearer for the user to apply this. Because when the effective shear span is equal to 4D, then you see ACS here in this formula 8.9, it's 4D. So the mechanical shear span is always smaller or equal to D. And that makes sense. In this formula, you will see GDG that we talked about, which is the size parameter, and it gives an indication of the roughness of the crack zone, the roughness of the crack zone, DT. Something to mention is that you can replace D by the mechanical shear span, but apparently only in formula 827, not for the other formulas when the D is there in relationship to shear force. So it's not very clear, but the interpretation until now is that D can be made equal to mechanical shear span only in the formula for the shear stress capacity of the concrete alone. In presence of actual forces, any D, the value of D in formula 827, remember this formula that we've just seen now, should be replaced by KVP or use formula 832. So we now know already D can be replaced by a mechanical shear span, but it can also be multiplied by a coefficient KVP as soon as actual forces come into the picture. This factor KVP is equal to this formula, again, dependent on the effective shear span, let me always bigger than 0.1. Or if you don't use this, so if you don't multiply D with this coefficient to take into account actual forces, you can also try to work around it by formula 832, which is a little bit similar to the one of the present Eurocode. It's you add or you subtract, depending on the sign of sigma CP, a portion of the actual force, of actual stress. So the basic concrete shear force stress of capacity should be deducted by K1 sigma CP. Sigma CP is of course the actual force divided by the section, cross section, and any D is negative for compression and positive for tension. The tau RBC0 is in fact the same as this formula here. You see it's the same formula, 833 is the same as this formula. But it's strange that 827 is this formula, 833 is this formula, it's the same. So why do they give it two different numbers? It's a little bit of a riddle. And 827 has a lower limit, which is tau RDC min, the minimum value. But in the formula 833, the lower limit is not there anymore. Yeah, you can say, because in formula 832, there is a lower limit, but this is the lower limit on the total, not on the first portion only. So it's not consistent. And then the factor K1 is given by this formula. Again, the effective shear span is appearing in this formula, and the eccentricity of bending moment and normal force or actual force. And the factor K1 has an upper limit of 0.18 times this value. Comparing this with the present Eurocode of 2004, we know that then K1 sigma CP with K1 was equal to 0.15. Only 15% of the actual stress could be subtracted or added. When we look at the K1 value, the upper limit, then AC equals B times H, and H is D over 0.9 for beams. You can say that the effective depth is 0.9 times the depth of the beam. Then you got the B, you can can scrap it. So you can see then that's 0.18 divided by 0.9, because Z is 0.9D times 0.9 gives you 0.22. So this means that the maximum allowable stress that you can deduct or add up, depending on tension or compression, to the shear capacity of concrete, that this has been increased by 50%. So if you remember the first video on shear, then you see that the calculation of the RDC was was too pessimistic in the present Eurocode 2 of concrete. So this is now rectified by this coefficient. Now, what's following is the comparison of the shear stress capacity or of the shear force capacity of the concrete alone, and also of the minimum value of it, according to the 2004 version and the new version of 2023. And doing so, we will generate a small database or with some parameters, and we will make a variation of all those parameters. We take a width of section of 300 millimeters. The diameter of reinforcement is 20 millimeters. The diameter of stirrups, 10 millimeters. The smallest value of the upper size, d lower equals d max, is 32 millimeters. The concrete cover will be 40 millimeters, and the steel quality, the value Fyk will be 500 megapascal. The tension reinforcement, taking in the formula to calculate rho L, we will take the tension reinforcement as the optimum reinforcement that is needed for the bending moment. And the optimum reinforcement is defined when the strain in the concrete is equal to the maximum strain in the concrete, and the strain in the reinforcement is equal to 1%. So this is an optimum use of materials, more or less. So we call this optimum reinforcement. The effective depth of the section is then the total depth minus 60 millimeters because of the 40 millimeters here and the 10 millimeters here. Then you have 40 plus 10 is 50 plus half of the diameter of the reinforcement. So we assume only one layer of reinforcement. That's for the data. The depth of the section, we will make a variation of 200 up to 1600 millimeters to have a simulation of more or less a slab or small depth beams and high depth beams. And the concrete quality will make a variation in the total range of 12 to 90 megapascal. I did not take into account 100 megapascal because for 100 megapascal I cannot make a comparison with the present version of the code 2004. So I make comparison between 12 up to 19 megapascal as concrete quality. Take now this graph. On the x-axis, we have the concrete depth of 200 up till 1600 with a concrete quality of C30, which is 30 megapascal. And on the y-axis, it's the ratio of the shear stress that the concrete can take, but it's the minimum value of the shear stress that the concrete can take divided by the minimum shear stress of the concrete of the version 2004. Looking carefully at this graph, then you will see, for instance, for a beam 600 depth and 300 width, you have already an increase of 40% in the minimum value of the shear stress capacity of the concrete. For small depths, you have more minimum shear reinforcement, much more pronounced than in previous cases. It goes even up 2 times as more. This change in slope, sudden change in slope, did it just because of the scale factor K in Eurocode, the present Eurocode, around there's a minimum value on the factor K, and that's why this point difference. In reality, I only calculated the point 2 points. That's why it's a straight line. But if you vary it from 200 to this value, then you will see it will slightly bend out, but the difference is negligible. This is just because I only had 2 points there and there. You see also that the minimum value of the shear force capacity of concrete alone is always bigger than 1. Bigger than 1, the ratio. So we always have more minimum shear capacity. Interesting to know that the ratio, which is on the y-axis, is in fact independent of FCK because in both formulas FCK can be scrapped. We will look now at it in a different way. Those two graphs have the same y scale, the same scale is 1000, 1.8, 1.8. On the y-axis is the shear resistance of the concrete alone, and on the x-axis is the depth of the sections from 200 to 1600. The width of the section 30 centimeters or 300 millimeters, and this graph is for the concrete quality of 30 megapascal. The other graph is for the concrete quality of 90 megapascal, so lower limit, upper limit. And we see immediately that it's more or less the same type of graph. Because of the scale, you can see now the difference, which is logic. And when the depth is smaller than 700 millimeters, then we have a higher resistance in the new work in 2023. So we have a higher resistance against shear that the concrete alone can take. When the depth is larger than 700 millimeters, then we have a lower resistance because the blue line, which is a version of 2023, is below the red line, which is 2004. So for large beams, we have a lower capacity. For smaller beams, we have a higher capacity, and for very small beams, the capacity difference is much more pronounced. Now we will rearrange our data, and we will make a graph of the shear stress capacity of concrete alone in megapascal, expressed in megapascal, and on the x-axis the concrete quality. And you will see for a beam of 300 millimeters depth that the blue line is the one according to the code in version 2023, and the red one is the one of the present code. You see immediately that for high strength concrete, there is a deviation on it because of the different values of the concrete strain at high strength concrete. We can make the same graph for a depth of 300 millimeters, a depth of 600 millimeters, and a concrete in a depth, beam depth of 1000 millimeters. And then we will see the evolution of the graphs. We see that for small depths, we have an increase of more or less 20%. on the capacity, the concrete stress capacity. For a beam of 600, it's more or less the same for normal concrete, but it differs for high strength concrete. And for beams with a depth of 1000 millimeters, for instance, we notice as a mean, more or less, a decrease of 7 and 2%. So it depends on the depth of the beam, what the maximum capacity can be of the concrete alone against shear. This graph was made for d lower equals to 32 millimeters. But there is one remark: when calculating the concrete capacity for the shear, then we have to put in some longitudinal reinforcement. We have taken this longitudinal reinforcement as the optimum reinforcement, but for high strength concrete, there's a different way of calculating the capacity, and that's why the reinforcement of the longitudinal reinforcement is different in 2023, in the version of 2023, regarding the version of 2004. This is logic in the sense that we calculate the resistance of the beam at optimum reinforcement. That's it. But at the other side, it's not that logic, because you compare two different things. So we will look into the matter now when the reinforcement for high strength concrete, the longitudinal reinforcement, is taken the same as the one which we have used for the version of 2004, and see what is now the influence. So for concrete quality bigger than 50, the reinforcement is different, and that is now here in this graph, the blue line. And the blue line is the shear force capacity for in the version 2023 for a beam of a depth equal to 600 millimeters. This graph is also made with d lower equal to 20 millimeters. The y-axis is the shear stress capacity on the concrete alone, and on the x-axis is the concrete quality. The green line is now the one where we put for high strength concrete the same longitudinal reinforcement. It is the reinforcement as prescribed in the version of the present version of the Eurocode. And you see now, when we compare everything to the present version 2004, that's the red one, then you will see for normal concrete with a quality smaller than 50 megapascal, there's no difference at all for a beam of 600 millimeter depth. And then what we wanted to demonstrate now is that the difference between the blue and the green line, you will see that we have an impact of 10%. So this is the impact because we took different amounts of longitudinal reinforcement. So the reality, if you want to make a proper comparison, will be between the blue and the green line. So there's not so much difference. What we haven't done yet is showing what is the influence of d lower on all our calculations, because d lower is a new concept. We made a graph again, concrete quality x-axis and shear stress capacity again without shear force reinforcement, and we compare everything with the red curve, which is the one with the present version 2004. That's the red curve, and the greens from light green to dark green. The light green is for 16 millimeters. Then we got 20 millimeters and 32 millimeters. So 16, 20, and 32 millimeters. So you'll see immediately that there is for high strength concrete, and even for the other concrete, you will have a significant difference in capacity. So the influence of the choice of the lower is there. And this is in absolute value of in megapascal. If you now take the ratio of the shear stress capacity with D lower equals to 32 millimeters and D lower equals 16 millimeters, then so it's everything divided by the light green one. Then you will see that you have a difference of 9%. Let's round it up to 10%. So the choice of D lower between 16 and 32 gives you 10% less or more capacity. So this is significant, and that's why you should be careful in choosing D lower in the design phase of a project. So when D lower is not exactly known, you must be very careful. And I recommend, because of that difference, the 10% difference, I recommend to use 16 millimeter for D lower, but of course the max in this case must be larger than 16 millimeters, of course. But when you take D lower as 16, then you are putting yourself on the light green curve, and then you know you are safe. A beam in a building has, in many cases, reservations into the beam for pipes or other elements that are going through the beam, and you can now neglect, in fact, the openings in it, on the condition that when the dimensions of the opening are both smaller than D over 6, than the effective depth over 6, then you can calculate your shear force resistance or your shear force capacity without shear reinforcement. You can VRDC, and you can calculate VRDC with D equals the value that you should obtain in a section without the reservation. So that's interesting to know. For instance, for a beam of 600 millimeters, then the reservation cannot be more than 100 by 100 millimeters. And in this case, when it's no more than 100 times 100 millimeters, then you don't need to take that into account in your shear force capacity calculation. On the other hand, when the dimensions are more than D over 6, then you should use the D in your formula for shear force. You should subtract from that D the maximum of the height of the depth of the opening, or the height of the opening, and the width of the opening. This means that when the width of an opening is bigger than the effective depth of the beam, that you have no shear capacity at all, because when D minus the maximum of H and W is D, then D minus D is 0. So there is no shear capacity without shear reinforcement, of course. And don't forget that we are talking here about VRDC. So this is interesting to know, that once the width is bigger than the effective depth, then you need to take other measurements to design the section against shear. When you have pipe bundles or different openings, one to the next, then when the clear distance is smaller than the effective depth divided by 4, then you should treat this opening or reservation as one reservation. So that's also something interesting that you can use in your in your design of buildings.